Calculate the momentum as seen by a stationary observer provided to a rocket ship with a rest mass of 1,000 kilograms as it goes from rest up to a speed of 0.99 c. Assume Gedanken conditions exist in this example. Okay, so we need to consider our Lorentz factor because we're traveling at 99% the speed of light. Right? So we do need to consider it. So our Lorentz factor is going to be 1 over 1 minus, v squared on c squared. I should rewrite that, shouldn't I? Just put 0.99 squared. Square root of all that. Okay. And if you put that into your calculator, I think that comes up with about 7 or something like that. If someone could do that for me, that'd be great.
So is there some kind of easier way to do it on a green calculator because it's really hard to get the correct notation?
What I kind of way to do it is to just open the bracket, put in the 1 minus factor, close the bracket, and put it to a power of -half.
Oh, that's a good idea. Good idea, yeah.
Yeah, it's 7.08.
7.08. Thank you very much. So a Lorentz factor of 7.08. So to work out, what do we want? We want momentum. Okay, we can do this. Remember, our momentum is just equal to our Lorentz factor multiplied by mass multiplied by velocity. Our Lorentz factor is 7.08. Our mass is 1,000. And our velocity is 0.99 times 3 times 10 to the 8. Okay, 0.99 times the speed of light. And we should get a big number here, I'm assuming. Big number. It will be. Okay. So I get 2.1 times 10 to the 12. Yep. Excellent. 2.1 times 10 to the 12. Now this is momentum. So kilogram meters per second. Okay. So this number here, this is sort of meaningless to us. That doesn't, I mean, it's really hard to visualize what that means. But part B is quite interesting. So if we take twice that momentum and apply it to a stationary rocket ship, calculate the final or the new final speed of that ship in terms of c. All right. So that's where you're going to need that equation from the other page. I've got to find it now. I can never remember that thing. Here it is. So our velocity is equal to p over m square root 1 plus p squared on m squared c squared. Okay. So that is our equation. So our p value, our momentum, is twice what we've got up here. So our p is 4.2. 4.2 times 10 to the 12. We know our mass is 1,000. And so we should be able to just put this all in to our calculator. So C is the speed of light. Yep, 3 times 10 to the 8. And again, this calculator is problematic. If anyone has an answer, I'd love to hear it. So when you put this in, you should get a meters per second value. We can convert that to in terms of C afterwards. Okay. Any takers yet? Yes. Good. That's what I got too. There. So you'll get 2.99 something times 10 to the 8 meters per second, which if you work that out, if you work it out as a, if you do this divided by c to get it in terms of c, you'll get it as 0.997 c. Now this is really interesting. Right? The really interesting effect here is at 0.99 times the speed of light, we have a certain momentum. But if we double that momentum, it only goes up, our speed only goes up by another 0007 times the speed of light. I'm sorry, 0.007 times the speed of light. So we have to put in a lot more momentum to get a tiny velocity change. And this is why we'll never be able to get actual masses traveling at the speed of light, because you need to put in infinite amounts of energy to get them to hit that C value. The closer you get to it, the more energy you need to put in to increase even a little bit. That's the point here. Okay, by doubling the momentum, we only increase our velocity by 7 parts in 1,000. Okay, tiny amount. Okay.